So in this course, having covered various operational modes of transmission electron microscope and understanding the physics behind image formation, and also looking at different kinds of examples and some brief tutorial sessions on how to obtain and analyze data, I'll give you in this particular lecture some examples of more recent developments in the techniques of electron microscopy, in particular in situ electron microscopy. This field has been there from very beginning, or let us say close to 50 years now, and more recently with the development of MEMS devices, the field has advanced rapidly. And in fact, when I say that this is a recent advancement, this is already close to 20 years old now, and we are heading into more and more interesting developments in the area of electron microscopy, where you are trying to bridge 2 or 3 techniques together. This is slightly old in terms of when the technique was developed, because now there are modifications being done to the instrument columns to enable ultra-fast imaging by introducing a laser in the microscope, or there are several other developments where, for example, there is development of atom probe tomography combined with TEM in the same column and things like that. So here I'll show you an example of how you can use transmission electron microscope as a sort of a micro lab by using MEMS devices. This is largely a part of work we've done at TU Delft, but this gives you a nice overview of how you can apply transmission electron microscope as a technique beyond just regular imaging and post-mortem analysis. This work has been done at several places, including IIT Hyderabad, Forschung Centrum Jülich at the Ernst Tuska Center, and at TU Delft at the Kavli Nano Lab. And these were prototypes which were developed long ago, and they are now available as commercial products through dense solutions also. So let us have a look at what this interesting area of in situ electron microscopy is, and how can MEMS devices help you plan experiments which are sort of very interesting and you only can dream of. So in conventional TEM, we know that imaging is typically post-mortem. Here is an example of a sample that we studied where you're looking at nuclear glass. This is a borosilicate glass, and on exposure to water for various periods, that is, here is an unexposed specimen, and this is exposed to water for 1 day, and this is for 1 week, and this is for 1 month and 3 months and beyond. What we did here was, there was some problem of what kind of chemical composition change is happening within a glass. One would not expect much changes in glass which is very stable, that too in presence of water, but there is an interesting mechanism that is observed called as dissolution and reprecipitation, which happens at the glass-water interface, and there is formation of so-called phyllosilicates, and they start appearing like fibrous kind of layers at the glass and water interface, and because of this there is a sort of a new mechanism of corrosion of glass as well, and this was possible to study by using STEM HAADF and combining with energy filtered TEM mapping. So a big challenge is visualizing light elements in transmission electron microscope, particularly the elements which are very low in atomic number, and we could see that boron and silicon could be mapped pretty well, and there is some kind of an alteration in the boron composition here, and that was quite interesting. So here is an example of application of electron microscopy techniques to reveal details where you would not quite often think that would there be corrosion of glass at all. So this is post-mortem analysis, and this is imaging under static conditions. How do you image changes in material in real time in a transmission electron microscope which is operated at ultra high vacuum? So to answer this, there are different approaches. One of the simplest approaches, you can modify the instrument. This was a methodology developed in York University and also in Arizona State University. It was Renu Sharma and Pratibha Ghai and Peter Crozier and a few of them who came up with the concept that in the electron microscope, the specimen goes in the objective lens area, and if you can isolate this particular region by using differential pumping apertures around the objective lens, so this is how a differential pumping aperture looks like. You can introduce a gas around the specimen and you can heat the specimen and you can see some kind of reactions that happen. So this kind of a modification to transmission electron microscope where you can introduce gases into the microscope column is actually called as Environmental TEM, and it gained quite some popularity, and it is very useful for some studies, in particular catalysis and chemical reactions that are typically with a material and gas environment. But the main limitation here is the pressures that you can achieve for the gas that you introduce into the microscope column is typically limited to the order of 10 millibar. So this is not really like the ambient conditions where chemical reactions typically happen. So this is one of the limitations of the environmental TEM, that you cannot go to very high ambient pressures. But then the other way in which you can have in situ experiments in the TEM is you use special TEM holders. So this is how a standard TEM holder looks like, and within the TEM holder, if you introduce two halves of grids, so here the very first attempts were done by using polyacrylonitrile membrane grids which were sandwiched one on top of the other, and in this gap the specimen you want to study, typically a liquid kind of a specimen, was introduced, and studies were done as early as 1970s only. And the idea is you form a kind of a couple of this membranes together and you sandwich them, and then you can isolate this from the rest of the microscope vacuum and you can see changes inside the material. Now, the idea of MEMS based devices, especially for environmental studies, is somewhat close to this kind of a system where you have two half cells in which the bottom and the top cell actually have silicon nitride membrane, and you introduce the specimen in between this and you can see how chemical reactions happen. So both the methods, whether you're using environmental TEM approach or a two half holder based approach, has its own advantages and disadvantages. So if you look at the more recent advancement which started around early 2000s, is studies based on MEMS based devices. The group from New York, when Professor Francis Ross was there, started exploring these kind of devices based on electrochemical cells, and they produced these sort of devices along with a company called Hummingbird, and then prototypes. There were lots of work being done with the group of Professor Niels de Jong and so on. And simultaneously in Delft as well, there were developments where studies were done using MEMS based devices. So the idea is, using clean room processing routes, if you have chips like this, where on the bottom chip you have some kind of an electric circuit, and in this case it is typically a heating spiral, and you place a specimen on top of this, and you have a silicon nitride window on which you have a kind of a heater which looks like this, and you close it with another top chip, and the bottom chip has an inlet and an outlet as well. If you seal this whole assembly and introduce it into a TEM holder, you actually can have an environmental cell. So if I zoom in closely into these windows here, the bottom chip contains of a spiral like this, and the top chip has these sort of pillars which are spacers to maintain the gap between the top and the bottom membranes. And these dark circles that you see here are actually thin silicon nitride, which is about 20 nanometers thick. That is the same case here. And here you can see that the specimen is actually a fib, a lamella. And when I close the bottom and the top chip together and align them, you actually can introduce it into the microscope column through the holder like this. And the holder has inlet and an outlet like this, and you can pass a gas through the nanoreactor assembly, and this is actually called as a MEMS based nanoreactor. So if I show you what can be done with this kind of a chip, just by using the bottom half of the reactor, you can use this as a simple heating holder. And we tried to do some interesting studies where we tried to follow the growth of precipitates in aluminum alloys while heating the specimen to an elevated temperature in the microscope column. So what was the interest in looking at aluminum alloys? Aluminum alloys are known for excellent strength to weight ratio, and these actually are also extremely corrosion resistant, and they are used in various automotive and aerospace applications. With their excellent passivation and strength to weight ratio, they are prime candidates for automobile and aerospace applications. And the reason why they get the strength is formation of these sort of precipitates within the aluminum matrix. And these are actually copper-rich precipitates which are formed in aluminum matrix. And what we try to see here is it possible to follow the growth of these precipitates in real time inside the transmission electron microscope? So the idea is, we prepared fib specimens and heated them to the supersaturated condition, where we elevated it to a temperature beyond 500 degrees centigrade. So this is called as solutionizing. And you create a supersaturated solid solution, and then you cool it to room temperature, and you start heating at elevated temperatures, and this process is called as aging. So we tried to simulate the aging treatment in transmission electron microscope by heating the specimen. This is by heating a specimen at 225 degrees for about 10 minutes. You see that as you start heating, there is formation of some kind of pillars inside the matrix here. These are actually copper-rich precipitates, and as you can see, there are different families of precipitates here. There is one family of precipitates oriented in this direction, and there is one family in this direction, and there is the third family which you do not see it, but it is coming out of the direction of the plane here. And when you hold it isothermally at 225 for 10 minutes, this kind of a treatment is actually called as aging of aluminum alloys, and you see the growth of these precipitates. So if I follow the heat treatment cycle and then there is the problem of projection limitation in transmission electron microscopes, and whatever you see is actually a projected image of a three-dimensional structure. So if you do something called as STEM tomography, this is a technique similar to CT scan that you do for any kind of biological investigation. You actually orient the specimen at different angles, and while you're tilting, you're simultaneously acquiring STEM images. And as you can see, when you're tilting through, you can see that there are different families of precipitates here, and at one point they look like spots here, and at one direction here they appear like some rods. So by obtaining series of these images and trying to do a three-dimensional reconstruction, what you get is a tomogram like this, and you can see that the precipitates that are formed are actually spanning across the thickness of the specimen. Now this is an interesting result because usually when you are looking at heating or these kind of processes in a transmission electron microscope, we know that the thickness of the specimen is typically less than 100 nanometers. And when the thicknesses are so low, your surface effects are more predominant. And when you heat, there is a greater chance that the precipitation actually happens on the surface. So one question that arises is then, why is there no surface dominated precipitation, and why do these precipitates span across this thickness, and why are they appearing similar to bulk heat treatment conditions? We'll look at the answer in a couple of slides, but this was an interesting observation. And if you look at how the evolution of the precipitates is, I was mentioning that there are three families of precipitates. Here are snapshots from that movie which was heated at 225 degrees centigrade, and if you look at the frames after 300 seconds and after 840 seconds, the arrows marked in green belong to one family, the red are one family, and the blue ones are one family. And it is interesting to note that the ones which are marked by red, if you look at the kinetics, are actually starting to grow far ahead of the other two. So that is approximately a minute before the other precipitates start nucleating. The reason is, if you notice here, the precipitates are connected by something which appears like this, and over here also you have these kind of features here. So within a face-centered cubic metallic material like aluminum, there is usually a large number of dislocations, and with high dislocation densities, these interfaces act as regions where precipitation is favored. So the dislocations are sites where the solute, that is copper, can be trapped much ahead of the rest of the locations within the matrix. So if you want to see the processes like precipitation, there is the process of diffusion, and then there is process of creation of vacancies or defects where the solute atoms are actually trapped, and that is where nucleation starts. So nucleation of these precipitates has started on dislocation surfaces before the other regions in the matrix, and that is why you see that the family of precipitates which are marked in green and blue start more or less around the same time, whereas the ones in red which are nucleating on the precipitates on the dislocations actually start much ahead. And if you look at it, the thickness of the specimen here is 140 nanometers. This is actually on a higher side. But what is interesting to note is this particular process of precipitation actually follows the square law of diffusion, So what you see here is, when I plot the square root of time versus the precipitate dimension, it follows a linearity. So this is what is observed typically for bulk diffusion, and when you look at the parameters here, the mean free path of diffusion is proportional to the square root of time. So this actually shows that this particular case has a situation where the heat treatment processes and the precipitation and the growth processes are very much comparable to what you can observe from a bulk specimen. So this is something which is interesting, and like I pointed out, it was in a thicker specimen. And after this, we thought, can we go one step further and can we do high resolution studies on this? And this was a study that we did in collaboration with a colleague who was visiting us from China, so Dr. Chunhee Liu, and a set of model binary copper alloys were actually prepared, and supersaturated solution of aluminum copper was heated at around 160 degrees centigrade. And the image that you will see now is actually an HR stem micrograph of aluminum matrix, and you can see here all these dots here are actually aluminum oriented at 001 direction, and these plates you see here are brighter. So this is STEM HAADF mode. So what you see here are copper rich precipitates, and once you start heating, you would see that these precipitates start growing, and at some point the precipitates which are actually smaller than a certain size, they kind of dissolve and they contribute to the growth of this precipitate which is already growing. And if you go further beyond, you can see that there is a change in the intensity of these precipitates quite strongly, which indicates that there is a strong copper addition happening. And you can also see that at various regions there is this kind of cloud-like appearance which kind of gives you an indication of the solute being diffused towards the trapping site, which is the precipitate here. So if you look at the time scales of how this process was happening, it is approximately 2 seconds per frame, and the temperature is at 160 degrees centigrade, and it was recorded in STEM HAADF mode. And if you see, at about half an hour, you see precipitates which are growing like layers like this, and after about 5 hours it grows even further, and at this early stages this has a crystal structure which is more or less like tetragonal, and as you age further it starts forming something called as theta prime, which is an intermediate precipitate. And when we did some DFT calculations, we observed that there are different stages of this particular precipitate. It is pre-theta prime 1 and then pre-theta prime 2, and then we had another layer like this, and there is a transient stage which is prior to the formation of an equilibrium precipitate. So by looking at these kind of processes in real time in transmission electron microscope, you get an idea on the crystallography of the system that you are looking at while the changes are happening in real time in the microscope. So you're already going one step beyond what can be done in conventional TEM. So this is one of the initial studies where at high resolution we were able to successfully look at a link between different stages of precipitation on the same specimen from the same location. And this gives you a lot of valuable insights into the material properties. Now the question is, there have been heat treatment studies done for a very long time, and why does it work in this particular case, and why is it similar to what you can expect from a bulk behavior? So the image you see in the background here is precipitates of copper which are on surface, and again going back to the question, why does it work? It is because primarily it is the mode of imaging, and furthermore it is controlled heating. The entire specimen is at the same temperature, and the specimen thickness is about 150 nanometers, which is on slightly higher side than conventional specimen thicknesses you would want for high resolution imaging, and more or less the specimen is at uniform thickness. So how do these factors play a role, and why is it important, is what we'll try to see in the upcoming slides. So if you look at heating holders in transmission electron microscope, there are holders which can actually allow a 3 millimeter standard specimen. It is a furnace type holder where in the tip of the holder you have a small cavity like this, and this is typically a tungsten filament kind of a thing which is heated by resistive heating. There's a wire that goes in here, and if you see the specimen which is of the size of 3 millimeter when it is put in here and when it is heated, the power that is consumed is in the order of a few watts. Whereas if you look at the kind of the holder on which we have done this study, it is actually a MEMS based heating holder, and the heating area is in the size of a few hundreds of micrometer square. So if you look at the power that is consumed for heating this kind of a system is only in the order of a few milliwatt. Now, why is this important? The idea is once you are heating, the heat dissipation rate, if it is actually small and the power that is being dissipated is actually small, this gives you excellent drift stability. So because of this localized heating, you have very good drift stability. And the other reason, if you look at the root mean square kinetics that you saw for diffusivities, it is interesting to note that in these particular alloy systems where you had copper, magnesium, manganese and silicon primarily in the matrix, for an experimental time of about 900 seconds, we computed what the mean diffusion length is, and around the temperature ranges in which we were heating, you can see that the diffusion lengths would be of the order of this number. So making specimen thicker than 82 nanometers for copper for this particular temperature range would actually make it relevant and closer to the bulk observations. And that is why we could see that the precipitates that were formed are trapped before the copper diffuses out of the matrix or out of the thickness of the TEM foil. So this is why you can actually observe these kind of things. But is it actually the only reason, or are there anything more? And just having a thick specimen, is it good, or are there any other problems, is what we'll come to now. So when you have a thick specimen and when you have a grain boundary that is present within the field of view, because the diffusivities are actually not the same for grain boundary versus the matrix versus the surface, you can see that you can have these sort of artifacts where, apart from surface diffusion when the thickness is below the mean diffusion length, you can also see some changes in thickness happening here at the grain boundary. This is actually called as grain boundary grooving, and it is commonly observed problem in very thin specimens, and this can always happen with very thin specimens. So how do you counter it? You maintain the specimen thickness such that half mean diffusion length is less than the thickness of the specimen. And if you now do compositional mapping around this kind of a region, there's another specimen at a triple point. You can see this is imaged in STEM mode, and if you take the EDS mapping from the same region, you can see here there is a variation in the thickness, and this actually appears like a groove. And if I see the specimen and a grain boundary here, there is formation of a groove here, and that is what you're seeing in this particular image here. So from the mass thickness contrast, you can see that in HAIDF mode, this is appearing slightly darker here because the thickness is reduced, and then in EDS map as well, you can see the presence of a groove here. So this is one of the problems you would have, especially if you have large grain boundary area. Your grain boundary diffusions also play a role in the material that you're studying. And then if you look at the specimens where the thickness is not actually uniform, if you see, we intentionally created specimens where we had two grains within the specimen, and because of different milling rates owing to the orientation differences here, the thickness of this particular grain is different than this particular grain here. And you can see that in the thin regions, when you heat the specimen to an elevated temperature beyond 500 degrees centigrade in this particular situation here, you can see that the surface diffusion is so dominant that the specimen kind of becomes like this, and you're left with the aluminum oxide shell here. So not having uniform thickness also prevents you from actually making observations that are relatable to the bulk effects that you typically see. And next, the question that arises is, when you're constantly illuminating with an electron beam, how does the local temperature change and what is the effect of the electron beam? The answer is, it certainly does affect your specimen, and you can see that in this particular case, when we are trying to obtain EDS maps from this particular region, beam currents even as low as 35 nanoamperes, or depending on how you are describing it, as high as 35 nanoamperes, it can start forming holes within this particular aluminum specimen, which is about 150 nanometers thick. So how do you counter the influence of the electron beam dose is prepare a couple of specimens and place them on the heater such that one of them is exposed to the electron beam continuously and one specimen is not exposed to the electron beam, and thereby you can draw comparisons after you've seen a change within the material. So having a reference sample, doing control experiments, and doing prior ex-situ experiments before in-situ studies always helps. And then the next question is, how do I know that the temperatures I'm actually heating to are corresponding to actual measured temperatures? Because one of the issues that you might think of is the calibration of these MEMS heaters that has been shown could be quite off. So to understand this, if you look at the heating spiral and if you place a phase change material like copper 3 gold here, so copper 3 gold is an interesting material. It has order disorder transformations, and if you see at room temperatures, it is more or less an ordered structure, and the ordered structure appears like this. And when you start heating to a higher temperature at 400 or beyond the critical transition temperature for this particular order disorder transformation, it actually becomes a disordered structure which appears like this. So here you can see this is appearing like Cu3Au oriented along 110 direction, and over here as well. And if I look at this in diffraction mode, the presence of these superlattice reflections actually indicates that this is actually an ordered structure at room temperature, and at around 400 degrees centigrade, the superlattice reflections start disappearing and they're completely gone. In fact, when you look at the series, we noticed that when you plot the temperature versus the intensity where this particular spots start disappearing, we noticed that this was around 379 degrees centigrade, and the transition temperature for this particular order disorder transformation is around 389 or 385 to 390. So you are more or less within a 10 degree centigrade range of the temperature. So the calibration of these MEMS heaters is also pretty fine. And we've actually also done some alternative methods to calibrate this. So by putting some polycrystalline silicon on the heater and heating it, by measuring the Raman peak shift, we actually calibrated how the temperature varies, and it follows this kind of a quadratic. So in this particular MEMS device, what you have is you have a heating control system in which you can input the parameters in such a way that you enter some values for these coefficients and you know which kind of a curve this particular heater follows, and thereby you can actually calibrate them. And with these calibration curves, you actually are sure that you are more or less within plus minus 5 to 10% depending on where you are placing the specimen. Right at the center, it is pretty much accurate, but as you go farther away, the temperatures drop by around 12% from the center, and newer designs of heaters are actually being produced to actually compensate for this. So this is an example of a MEMS based heating system, and this will give you an overview or an idea that you can use the transmission electron microscope to run some real-time experiments. Now this is a case for a bulk fib specimen, and we've done some interesting studies on looking at sputtered thin films as well, and we looked at spinodal decomposition problem in silver copper thin films. So the idea is, on the MEMS heater, if you deposit copper and silver from the back side of the heater, and the thickness of the film is about 40 nanometers and the composition is more or less 1:1, and you take them to the microscope and then start heating the system, you can see some changes that happen within the thin film. So if you see in the initial condition as deposited case, the silver copper film appears randomly oriented, and if you look at the diffraction pattern, it appears like sort of amorphous ring like a structure, but you have a single phase here and you have a sort of a broad first spot which corresponds to the 1:1 reflection of the silver copper alloy. When you start heating this material, you notice that as you start holding it isothermally at 400, there is a significant change in the grain size. So starting from something like this, all of a sudden there is this explosive growth in the grain size at some temperature, and if you check how the grain size changes with temperature, up to 200 degrees centigrade there is no change, and then initially around 225 you start seeing some grains start appearing, and beyond 250 there is a significant grain growth. So within this region below 250 degrees centigrade, there is something interesting that is happening, and if you plot the grain growth kinetics, you see that beyond 2 hours there is only grain growth and the grain boundaries are appearing more and more sharper, but all the interesting transformation or the phase separation is actually happening below 250 degrees centigrade. So if you look at the diffraction contrast obtained in TEM mode, you see the microstructural changes in the film, and there is no significant grain growth between 250 to 400, and you are looking at bright field mode, and it is predominantly dominated by diffraction contrast. So within this low temperature or between 550 to 200, you cannot distinguish whether there is some compositional variation here. So in order to understand this, you have to use other complementary modes, and for this we did imaging in STEM mode, and within 50 to 200 milliradians in STEM, it is essentially Z contrast. So we've seen in this course earlier that the intensity is proportional to Z to the power root 3, and that is what you see. So if you look at this particular specimen, the same region in STEM HADF mode versus bright field mode, you can see in the bright field mode, the features that appear here are significantly dominated by diffraction contrast, and you see a lot of twins. But the same thing if you see in annular dark field image, you can see that these regions are having slight darker intensity than this particular region, which is brighter. So there is definitely some compositional variation. So what you can do is you can heat the specimen inside the microscope while imaging, and by holding it at different temperatures you can obtain compositional maps and then see how the local composition is varying. So when you are imaging in STEM HADF mode by isothermal heating again, you can see that beyond 180 degrees centigrade, there is suddenly some change and phase separation that happens, and beyond 250, like mentioned in the previous case where we were looking at no change between 250 to 400, that is what you also observe here. And in fact, in the tutorial I tried to show you how these values of the domains that are actually forming can be measured in real time. The example of this by aligning the movie and obtaining the domain sizes was already shown to you. So you can notice that the sequence of which the phase separation happens is you have initially phase separation around 180, and then you have coalescence, and you also observe Ostwald ripening and coalescence of some of these silver rich and copper rich domains. So if you look at the kinetics of how the domain size has changed, beyond 250 there is no significant change in the domain size, but if you look at the area fraction, around 180 is when the phase separation starts, and we've done some collaborative studies to look at phase field separation and the temperature ranges, and the mechanism for aluminum copper kind of is in sync with the process called as phase separation by spinodal decomposition. So if you look at the compositional mapping by energy dispersive spectroscopy, at 50 degrees centigrade you do not see any variation in the composition. At around 100 to 150 also you do not see any changes, and from 200 onwards you can see that there is formation of separate domains, and at 250 this becomes more prominent, and the darker regions are copper and the brighter regions are silver, and this is what you see, and you can start mapping the compositional variations in TEM while you're heating and changing the specimen as well. So we were interested in looking at visualizing the onset of spinodal decomposition by isothermal heating, and the specimen was held at 180 degrees centigrade for some time, and you can see the timestamp here. And after about 70 minutes or about 40 minutes, you actually see that there is a significant domain size change that starts. And if I look at the snapshots from this movie, around 13 minutes there is already some phase separation which starts, and around 23 minutes these domains appear slightly larger, and this is how the phase separation is proceeding. And what we did is we tried to check if the sizes of these domains are corresponding to the spinodal wavelength, and we also wanted to verify whether there is uphill diffusion here. So the idea is, in case of uphill diffusion, if you take the mean intensity of pixels over mean intensity of pixels in all the frames, for all the 199 frames that we recorded, we measured in the regions where there are copper rich pixels with increasing time, there is actually a drop in the ratio of the mean intensities, whereas in silver rich pixels there is an increase in the intensity. And this is kind of an indication of uphill diffusion, because when the domain size is changing, you would expect the composition to actually increase, or when you look at conventional diffusion, there is always transfer or diffusion of material from a region where the concentration is high to a region where the concentration is low, whereas in this particular case it is indicative of something like uphill diffusion. And we also saw the percentage change of intensities, and you can see that this is an indication of spinodal decomposition. And we also try to follow these same within the temperature ranges mentioned here in diffraction mode. And as you can see, once you start heating at around 180, after some time there is some change and some of these spots start appearing, and I think at about 140 minutes onwards you see some spots already start appearing. And as I heat further beyond 200, there is a significant change, and what initially appeared like an amorphous kind of a ring, it starts appearing like a spot ring with two separate phases. And when you deconvolute these and do rotational averaging on the diffraction patterns, you can clearly follow how this intensity of these spots changes. And about 72 minutes onwards, we saw that there is a phase separation that has started at around 180, and at 130 minutes you see there is a significant fraction of phase separation. And this is what you can do in diffraction mode. And if you do analysis and deconvolution of these rings here, you can see exactly that the percentage formation of the secondary phase is proportional to the compositional variations that we actually observed with EDS as well. So by doing these kind of in situ heating experiments, we've seen that in one of the bulk heat treatment cases, like in aluminum alloys, you could follow the onset of precipitation and you could follow the nucleation and growth of these precipitates. On the other hand, in this kind of thin film system, you can actually do very interesting phase separation studies, and these thin films are in particular useful for looking at sensors based on surface plasmon resonance. And with controlling temperature and domain sizes, you can actually restrict the size of these silver domains which show a plasmonic behavior, and these can be used for sensors as well. So as you can see, the diffraction peak, which appears like a single broad peak here, starts separating out, and you see the formation of copper rich and silver rich rings here. And this is an interesting way in which you can do in situ heating to look at materials and understand material properties in real time in a transmission electron microscope. Moving on, if you recollect, I introduced that the MEMS based devices are actually a two-half system, and we only saw the application of one half, which is the heating holder. So let me just recall that the combination of the top and bottom chips, when assembled together and aligned and introduced into a TEM holder, you can actually introduce a gas, and by flowing a gas through the system, you can see what kind of reactions happen in the electron transparent region. So in this particular case, I'll show you an example on the aluminum alloy on which we introduced in the very beginning. How does the corrosion behavior look like when you try to do this in an electron microscope column? So the idea is, when you have the top and the bottom chip together, you can assemble the nanoreactor by putting it into some kind of an alignment tool. This was one of the first prototypes that we made. In fact, the very first version of the holder that we developed actually did not have the option to put an alignment holder into the alignment tool, and it was separated. So in this kind of a metal block, you had the bottom and top chip together, and with these micrometer screws, you were positioning the top chip on the bottom chip and moving it in the XY plane in such a way that you let the top and bottom chips coincide with each other. And when these two coincide, the region here is actually an electron transparent region. And in the next versions of the holder that we developed, we got in a holder into the alignment tool as well. And the idea is, you place the chips here and you seal on the top by just placing O-rings. You can actually get vacuum sealing in a reasonably good way. So in the beginning, we were actually gluing these chips together with water glass so that you could achieve pressures as high as 4.5 bar. But with the modification with the design where the chips are sealed only by pressing the top and bottom chip against each other and having a Vuitton O-ring in between, you can achieve somewhere around 1 to 1.5 bar pressure. So the experimental setup looks somewhat like this. This was one of the first versions that was developed. The inlet and outlet pressures on the holder tube are monitored. The holder goes into the microscope column like this. There is a small membrane pump with which you are pumping the gas out of the holder here. There are much improved and better versions of mass flow controllers with programmable valves and so on. But the very first version, we simply had a mass flow controller, and because we wanted to introduce oxygen bubbled through HCl at pH 3, so this round bottom flask here actually has HCl maintained at around 35 degrees centigrade, and by flowing oxygen through, and the tube here is then connected to the holder, and there is also a bypass valve in case there is a rupture of the membrane. So the idea is, when gas flows into the microscope, into the holder and the nanoreactor, you are having saturated oxygen, which is also containing vapors of HCl, or it's kind of an aerosol, and you can use this to study corrosion behavior. So having told that you can assemble the holders and so on, I just want to highlight a few issues that you can run into with these kind of setups. So firstly, when you're having this kind of gluing mechanism, the capillary force between the membranes that are very close is so high that if the gap between the top and the bottom chip is not adjusted carefully, you can potentially have the windows flooded with glue like this, and you lose your area of interest. And this water glass glue was used because it does not contain any hydrocarbons, and hydrocarbon contamination is a big problem for in situ gas experiments, and that is one of the reasons why we were using water glass, which is a sodium silicate kind of a suspension, and this suspension does not have consistency in the viscosity, and when the glue is not maintained, or if it is overexposed for a long time, or if it is not maintained in the right temperature condition, you run into these sort of problems. So the contamination of hydrocarbon and contamination of glue is a big issue. So if you're using a glued environmental cell, the success rate is extremely low. The contamination, if you're using oxygen as the system in which you're studying the reactions, it is not that big a problem, because whatever hydrocarbons are there, they tend to get oxidized in the oxygen environment and then they're sort of removed out. But it is mainly an issue for other gases. It is unavoidable, but you can use some kind of liquid nitrogen traps or filters, hoping that there'll be less hydrocarbon contamination. And gluing is not always successful, and in glued kind of systems, it is impossible to do post in situ analysis. The next design that we developed was in the top chip, we introduced an O-ring here, and we used an O-ring which initially appeared like this, but then we also used laser cutting to make an O-ring with a rectangular cross section, and this goes into the groove here. And when you use an O-ring, it actually seals the chips together when they're pressed, and beyond this, if you're also gluing, there is definitely no contamination from glue. The only reason you might want to glue is if you want to achieve slightly higher pressures, but when you glue, you cannot separate the top and the bottom chip out, and this can be used in either a static or a flow gas holder, or even kind of a liquid cell. But the challenge is, because of the thickness of this O-ring, it is not extremely good for liquids. So there are problems pertaining to contamination, gluing, assembly, rupture of membranes, and so on with these kind of gas systems. And I'll show you an example here, an in situ corrosion experiment where oxygen was bubbled through HCl and passed over a surface of aluminum 2024, which was heat treated in T3 condition. And as you can see, at two locations, this is actually near a grain boundary, and one of these precipitates gets dissolved, and at other locations in the matrix surrounding a combination of these kind of precipitates which are rich in manganese, iron, there is dissolution in the matrix. So this is actually a kind of a mechanism which is known for the people working with corrosion. This is called as de-alloying at a grain boundary precipitate. This is an anodic precipitate which is rich in magnesium, and this is a cathodic precipitate which is rich in manganese, and you see an attack in the matrix. So these are sort of mechanisms of localized corrosion, And then moving further, the thought was, if you can do heat treatment and then corrosion on the same specimen, how would it look like? And the answer is, if you heat a specimen at around 200 degrees centigrade, the way I showed you in the example earlier, these kind of precipitates start growing in the matrix. And on this same specimen, if you now close it with the nanoreactor, the top chip, and seal the nanoreactor and introduce oxygen bubbled through HCl, you can see that the entire surface, actually there is some kind of corrosion attack that is happening. So because in this particular case, the precipitates that are formed here are kind of sticking close to the surface, you see there is a significant surface attack. And because it is in a 2/2 nanoreactor where you are not gluing the chips together, you can separate the chips out and then you can do kind of tomography and see what kind of corrosion product is formed. And with this, you can use the transmission electron microscope with combination of these MEMS holders way beyond conventional TEM imaging as well. So with this, I can summarize that you can do all kinds of in situ studies these days, in situ heating, environmental and gas experiments. These are what I've shown you now. You can also do liquid cell experiments. So from heating experiments, you can get insights on how the crystallography and the composition is changing and how the mechanism of precipitation is actually happening. And from in situ environmental studies, you can also look at localized corrosion and onset of these kind of chemical changes. But I also introduced that there are several problems. That is, what is the success rate of these experiments? How representative are they of real conditions? What are the challenges? These are experimental, engineering, scientific, specimen related, environment related. So there are a host of challenges. What is the effect of electron beam? You'll always have this. And how reproducible are these experiments? And what is the effect of the surface? These are a few questions that I actually raised at different stages in the discussion that we had earlier. And to summarize, the issues with in situ TEM experiments can arise from the specimen, the system, and the mode of imaging. Please do not plan any in situ experiments without supportive ex situ studies. The issues with heating are surface diffusion, issues pertaining to specimen thickness, surface precipitation, and beam-induced effects such as beam-induced damage or localized heating. The issues with gases are predominantly contamination from the tubing or the system or the gas that you also use. You also have the issues with cracking of membrane. You have beam-induced chemical changes to the environment. And the issues in liquids, I've not covered liquid cells here, but you also have issues related to thickness, volume of the liquid, beam-induced effects in radiolysis, and so on. So most issues with gases and heating can be tackled reasonably well. Liquids, they are still challenging, and there is recently interest in using graphene as a liquid cell membrane. And if you're looking at two-dimensional systems like graphene or hexagonal boron nitride or membranes like that, you can use them to produce liquid cells where you have a static liquid and a nanoparticle, and these are sort of the most reliable reproducible liquid cells as of now. But there are also systems which help you maintain thickness of the liquid well, and with sort of pressure driven controllers, the flow rate of liquid and all are more or less being solved nowadays. So all said and done, in situ electron microscopy can be an exciting area, but do not think that every experiment can be done only with in situ electron microscopy. Please plan out proper supportive ex situ experiments and define a problem. Use in situ microscopy as a tool where you are looking to solve some specific problems which can only be studied with these kind of studies. So with that, I'd like to end this discussion, and I hope you got a flavor of what are advancements beyond conventional imaging in transmission electron microscopes. And with that, I think we are reaching an end of this course. I've talked about imaging modes, and I've also shown various examples. We understood mechanisms of how different modes of imaging in transmission electron microscopes work. We've also seen examples of applications and different kinds of case studies, and we also saw an extension of the technique to newer developments such as in situ microscopy. And in the next lecture, I'll be summarizing what we've covered in this entire course. And with this, I'd like to end this here. Thank you.